to stay around on the Zooms to at least attempt some kind of socializing, if you wish. So thank you and welcome to FSTTCS. Sorry for the delay. Thank you.
Yeah. Thanks a lot, Nikolai. Should we maybe start? I guess. Should we wait a couple of minutes, or shall we start?
I'd say we start because we're late anyway, and we want to pick up.
Yeah. Yeah. Nikolai, can you make Yoni and Debaran also co-hosts? Let me see if I can do that. Yeah. Okay.
They are co-hosts.
All right. Okay. Excellent. All right. Thanks everyone for welcome to this first session of FSTTCS in this one more virtual mode. It is all the more pity that for 2 times in a row now FST has been in one of the best locations in India, and unfortunately these are the exact 2 years, and these are the only 2 times FST has ever been in Goa, and unfortunately in both these times it has been online, so we have not been able to take advantage but as a result I hope the attendance has been higher because in Goa I think people would have maybe gone to the beach more often as well. After talks. Okay, right. So with that introduction, let's start the formal proceedings. The first session will be with 4 talks, and the first talk is on TPTL and in particular the expressive equivalence in the pointwise and continuous semantics, and it will be given by Nabarun. Nabarun, the floor is yours.
Okay, thank you. I'll share my screen now. Can you see my screen?
Yeah,
okay,
we can see.
Thank you. Thank you. Okay. So hello everybody. I'm Nabarun, and I'll present our result on the expressive equivalence of TPTL in the pointwise and continuous semantics. So what we do is we introduce a first order logic which we can be used for specifying properties of real-time systems, and we introduce the pointwise and continuous semantics for this logic, and we show that this logic is equally expressive in both the pointwise and continuous semantics. Now using this result we can show that the TPTL logic, which was introduced by Allure and Hensinger, now if we endow TPTL with a since operator, so which allows us to argue about backwards time propagation basically, if we endow TPTL with the since operator, then that logic is also equally expressive in its pointwise and continuous semantics. So our logic is interpreted over timed words. So a timed word is basically a sequence of actions from a finite alphabet of actions, and each action has an associated timestamp to it. So one illustration of a timed word would be something like this: an action A at time 0, A at time 2, then B at, let's say, time 2.5, and then B at time 3.8, and so on. So this is an illustration of a timed word, and at each timestamp we have one, at most one action. Now we use these constraints, which we call simple constraints, in our logic. So a simple constraint is either of the form and a variable x related to another variable y, or a variable x related to y plus c, where y is again a variable and c is a rational constant. Now what are the relations that we allow? These are the standard less than, equal to, greater than, equal to, and greater than. Now I'll give the formal syntax of our logic. So we call our logic the first order logic with simple constraints. We'll interpret it over timed words, which have a finite alphabet of actions, sigma. So the syntax is we allow the atomic predicate AX, which essentially says that at time X, the action A occurs. We allow simple constraints, and then we allow the Boolean operators not and or, and we allow first order quantification. Now, this logic can be interpreted in a pointwise and a continuous semantics. and the two semantics differ in the way we interpret quantification. So I'll illustrate our semantics with a few examples. So consider this formula: ax and x less than equal to 2. This is basically saying at time x an action A should occur and the time x should be less than or equal to 2. So for example, if we have this time word, then at x equal to 1.2, this formula is satisfied. And this is both in the pointwise and the continuous semantics. Now the difference between the pointwise and continuous semantics arises when we study quantification. If we have a there exists quantifier, in the pointwise semantics, we'll say that a there exists x, a formula phi, is true if it's true for some x which is an action point. That is, the value that x can take must be associated to some action in our time node. On the other hand, in the pointwise semantics, we'll say that there exists x, phi is satisfied if phi is satisfied for any time x. So there is no stipulation that x must be an action point. As an example, consider this formula. There exists x, ax, and x is between 0.5 and 1. Now, in the pointwise semantics, this is not satisfied because there is no action in the interval 0.5 to 1, which has the action a. This formula is not satisfied in the continuous semantics either, for the same reason that there are no action a in this interval. Now, finally, consider this formula. It says there is an x between 0 and 1, and there is no y, which has an action a associated with it, and y is between x plus 1 and x plus 1.2. Now observe, in the pointwise semantics, this would mean that there is an action point a, action point x, between 0 and 1, and the rest holds. Now the only action point between 0.1 is at 0. However, if we take x to be 0, the interval x plus 1 to x plus 1.2 does have an action a. So this sentence is not satisfied by this timed word in the pointwise semantics. However, if we interpret this into continuous semantics, then this timed word does satisfy this sentence, because take x to be 0.5. Because in the continuous semantics, x can take any time point as its value. It does not necessarily have to be a time associated with an action. So for x equal to 0.5, it is clear that the interval x plus 1 to x plus 1.2 is empty. So this illustrates that the two semantics are not trivially equivalent. So we need to do some work to show that the two semantics are actually equally expressive. So we'll use the notation.
Nabaran, sorry to interrupt. I think you have a couple of more minutes, right? So
yeah. Okay.
Yeah. Please try to wind it.
Yeah. So I'll quickly go through so we have the pointwise to so we give two translations. We give a translation for pointwise to continuous semantics and a translation for continuous to pointwise. The pointwise to continuous semantics is a trivial transformation. All we need to do is, for every quantified variable x, we need to stipulate that x is an action point. Then it is clear that in the pointwise and the continuous semantics, they'll behave equivalently. For the other direction, we have to do some work. So the first thing we introduce is a normal form. We introduce a normal form for our continuous semantic sentences, which are basically of the form there exists x, ax, and a conjunction of constraints, and then another formula which will be in normal form or negation of exists normal form. Here are some examples of sentences in normal form. Then we give our theorem. This is the first theorem, which says that any FOC sentence can be equivalently expressed as a Boolean combination of sentences in exists normal form. So we just need to work with for our sentences in exists normal form. So now how do we do the translation? The first thing we do is we identify variables as active or passive. An active variable is a variable which is quantified along with an action point. For example, x in this sentence and y in this sentence. A passive variable is one which is not associated with an action point. For example, x in this sentence. What we wish to do is we wish to remove all passive variables from a sentence. If we do that, then the sentence has only active variables, and such a sentence is equivalent in the pointwise and continuous semantics. So how do we eliminate passive variables?
Sorry, Nabaran, I think we'll have to wind up now.
Okay.
Otherwise, we won't have time for questions.
Okay.
Yeah, sorry about that.
Yeah. So in our paper, we give a method to eliminate one passive variable, which then we extend to eliminating all passive variables from a sentence. Hence, we get this theorem that any continuous sentence can be translated into an equivalent active sentence. And this shows that the logic is equally expressive in its two semantics. And finally, we give a theorem which basically tells that a TPTL with sense is equally expressive. For this, we convert TPTL with sense to our logic. We know it's expressively equivalent in our logic. Hence, TPTL with sense is also expressively equivalent. This is the end of the talk. Thank you.
Yeah. Thanks, Nabaran. Yes. So, are there any questions? I mean, we have time for, I guess, one quick question. Please unmute yourself or raise your hand if that's your style. Yeah, Nikolai, please.
So there's this paper by Joaquin Worrell and Paul Hunter about the expressive completeness of metrical temporal logic. And there they show that you can transform every formula into one such that at the end it boils down to local formulas and a bounded radius. I was wondering if that's useful in your work.
Yeah, actually, Mikola, yeah, I'm not. Maybe I should look at that paper. But so is that in a particular context of continuous or pointwise?
Yeah, it's continuous. Well, yeah, it's continuous, but I think the result might have wider applicability, that you can transform every formula so that the only measurements are done locally. That seems to be maybe
okay. And so maybe from there we could try to then translate it to a pointwise.
Maybe just something that came to mind. I'm not sure.
Yeah, maybe we should look at that angle.
Yeah. Okay. Great. Thanks. I think we will stop and move on to the next speaker now. Nabaran, could you please stop sharing your screen?
Yes, sure.
Yeah. So let's try to keep to our time. So remember that this is a really short session. We have 3 more talks. So I'd really appreciate if you could finish within the 8 minutes allotted, so that we have time for at least a couple of minutes of questions, and then a minute for the transition, right? So we're starting at 3:53. So I hope we will finish by the talk by 4:01. Thanks a lot. The next talk will be by Olivier Spietel. I guess his name right, and it will be on a local first order logic with 2 data values. Olivier, please share your screen, and the floor is yours.
It would work now?
Yeah.
Great. So hello everyone. I present my work on local first order logic with 2 data values with Benedict Bolig and Arnaud Sagnier. So the context is to have a logic with handle data values. So and the main application for us is we aim to distributed or concurrent system, and so we want to specify input-output behavior or distributed algorithm. So basically, if we have like a cloud of computing units, and so we will use first order logic, and so the structure will just be a set and 2 data value for each element and some labeling on the elements. And so the only thing we can do with the data value is to compare the equality of them, so we can think as identifiers. So a famous problem in distributed computing is a consensus problem. So we have any number, unbounded number of process, and they all suggest value, and they want to agree on one of the value which has been suggested. So here the value 1, 2, 3, and 1 has been suggested, and they all agree on the value 2. So more formally, we use so this is a logic we introduced as the final one. So yeah, just the same thing formally. So for the formula, we have for the syntax is a classic FO with a with label, equality, and the first order parts, and we can test for the equality of the data. So this says that the element pointed at X and the is data value is the same as the gis data value of the element Y. So, for example, yeah, here we can do the consensus problem in this logic. So it says that first the conjunction. So we say that there is exactly one element X with the leader label. So we can say exactly one in first of the logic. And the second part of the conjunction says that for every Y, there is an element X with the label leader, and that the input data value of X is the same as the output data value of Y. So this specifies a consensus problem. And we denote by FO2 the two variable fragments. So we interested in the satisfiability problem for this logic. So basically just according to some fragment F, if I give you some formula phi, is there, you answer me in saying is there a model which satisfies the formula. So for the whole logic is undecidable, even if we do not compare the input and the output. So basically this is what this theorem states. But hopefully the restriction to first order logic with only two variables is decidable, but still there is no comparison with the input and the output. And another related work is a data word, logic and data word. But on all this work, there is no comparison with the first and the second data value. So this is one of the main contribution. So to overcome the undecidability, we introduce what we call the local first order logic. So we start with, if we have a structure, we draw the data graph. It's a variation of the Geffman graph. And basically we connect every data value which are equal. And here we have denoted by A some specific elements in the structure. And in blue, we have denoted all the data value at distance 1 of the element. So we have in blue, we have the ball of radius 1 around A. And from this, we extract the Y neighborhood of A. So 1 is a variable we could replace by any integer R. And so what we do in this logic is that we have some formula psi into brackets. The one here is the radius of the ball, and X is the center. And phi would be any formula in first order logic. But the restriction is that it will only be able to reason about the neighborhood here. Okay, so this is the syntax, and yeah, so we have one decidability results. So this is the main result. So for radius 1, and if we are able to compare the input and the output in only one direction, so it's not the full results, because it will be really great if we could have the 1, 2, and 2, 1, but it's slightly technical to explain how it is possible to not be symmetric. But in this case, we were able to show the decidability, and so we reduce this to the satisfiability of FO2 over two equivalence relations. Okay, and we also show also show some undecibelity results. So if we are with radius 3 and we do not compare the input and the outputs, it's undecidable. And so if we augment the radius, it will be undecidable too. And for radius 2, with a comparison of input and outputs, it's undecidable too. So we do this by a reduction from the periodic tiling. And so it's a technique which is already well used to use a periodic tiling to prove undecidability. So the main achievements were to find a way to encode the plan into our logic. So it gives us this nice picture. So basically the green area has an element with the same first value and the purple area with the same second value. And so to complete the picture, we would like to consider both diagonal relation. To study some restriction on the quantifiers, so only the what we call the existential restriction, and develop some approximation methods. Okay, so that's it. Thank you everyone for listening.
Thanks a lot, Olivier, and thanks for sticking to the time. Are there any questions? So we can have time for 2 questions this time. Please feel free to lift your hands or unmute yourself if you do have a question. I do not see any lifted hands yet. Mikoy. So Mikoy, you could start.
Misunderstanding on my part, I guess. I didn't understand how it's different to have the 1,2 and the 2,1.
Okay.
How could that be different?
Yeah, hopefully there is a picture which explains this. So basically here, so see we have the elements with data value 1, 2, and here another one with the data value 3, 1. So we have we make that the edge is oriented now. So this, and it makes that this element is in the ball of radius 1 around this element, but it's not symmetrical.
So this is the asymmetry is the locality definition, not in the general non-local logic.
Yeah, it's in the definition, yes.
Yes, thank you.
Olivier, so is there a different way of defining locality which could be symmetric as well, or?
Yes, of course, and we did this because it was, to be honest, because it was hard. We didn't manage to prove in the symmetric case.
So that's an open problem, is it, or
yeah,
is it undecidable?
We do not know. We the trio of the author, we think that it's decidable, but we might be wrong. We might be right. We don't know.
All right. Okay. Are there any other questions? Yeah, Bartosz, please.
Okay, so I have a question. Do you know what happened, for example, if you allow for linear order on data values instead of just equality? This is a reasonable question.
No, we didn't think on this. No.
Okay.
Okay. Great. Let's thank Olivier again for a very short but good talk. And let's move on to the third speaker, who's Bartosz. Bartosz, could you share your screen? And you have, as always, 8 minutes with four questions. The floor is yours.
Can you hear me?
Yeah.
Can you hear me? Okay, great.
Yes.
So let me introduce myself. So my name is Bartosz Bednarczyk. I'm a PhD student at TU Dresden and University of Wrocław. And this is a joint work with Tony Tan from Taiwan. And this work is also based on the bachelor thesis of Anna Pacanowska and Maja Orłowska, written under my supervision at the University of Wrocław. Okay, so let me start with a motivating example. So in knowledge-based representation, we usually have knowledge bases, which are composed of two parts. We have a database part and a knowledge part, and the database in this case will be composed of citizens. So I can state, for example, that I'm a citizen of a given city. and that I voted for a person called XYZ. In addition, we will have a knowledge formalized in description logic-like language. For example, that every citizen voted for someone. And we would like to formalize the concept of a winner of the election, which can be done as follows. So for example, I would like to state that the winner is precisely this person that has at least 50% of total votes. So 50% of voted for predecessors, voted for relation to predecessors. And in our scenario, we must have two features of our logic. For example, we would like to express inverses of relations, and we would like to have some form of percentage counting. And unfortunately, there is no such logic available at the moment. So let me discuss related work briefly. So there are at least three logics that I know that can express similar things. So there is a Pressburger model logic by Stefan Demry and Denis Luquier. But the problem with this logic is that it cannot express inverses of relations. It can express percentages, but it cannot express inverses. The second logic is ALC with expressive cardinality constraints by Franz Bader. And in general, there is a whole family of algebraic model logic that can express percentages, or in more general setting arithmetic, but they cannot express inverses. On the other hand, we have two logics, namely ALC SCC++ by Franz Bader and the other people, and FO2 with Hartig quantifier. They can express inverses, but they cannot, and they can express percentages, but they are both undecidable. So we cannot use them to formalize this motivating sum. So in our case, we will focus on two decidable fragments of first order logic. The first one is the two variable fragment. So the fragment of first order logic in which we can use only X and Y. And this fragment is known to have the finite model property. So every satisfiable formula has a finite model. And the satisfiability problem, so also the satisfiability problem for this logic is known to be complete for non-deterministic exponential time. And this logic is not that trivial as we can reuse variables. So for example, with this formula, I can state that every element has an outgoing path of length at least 3. So I can quantify over X, quantify over Y, and then I can reuse X and I can reuse Y. Another logic that we will focus on is the guarded fragment, and this is obtained by relativizing quantifiers by atoms. And what I mean precisely is that whenever I would like to quantify over a tuple of elements Y, and I would like to state that phi of XY hold, I must introduce a guard for it. So I must introduce an atom alpha of XY that covers all the three variables from phi. And similarly for the universal quantifier. And here is the example. For example, I can formalize that some artist admires only beekeepers, and the formula in first order logic is as follows. So here I introduce X and I guard it with artist of X, and here I have beekeeper of Y, so I have an atom admires XY that guards the variable Y. And the co-example is as follows. So I cannot say in the guarded fragment that every artist admires every beekeeper, because okay, here I have a variable X and this is guarded by the atom artist of X, but here I have admires XY, so I must have a guard for X and Y at the same time, but here I only have an atom that covers a variable Y. And this logic, the guarded fragment, is also well studied. It has the finite model property, and its satisfiability problem is complete for doubly exponential time. Both of these logics can capture ALCI, so the standard description logic with inverses, but they cannot express percentage quantifiers, for example, because they are fragments of first order logic. So what we would like to do in this talk is to extend the logic with some form of percentage counting and see what happens. And we introduce percentage quantifiers under two different semantics. We have a local and global semantics. So for global semantics, we have quantifiers like this. So there exists exactly k% of X's satisfying phi. And it means that I check over my whole domain, I count these elements satisfying phi, and there must be exactly k% of them in total. Similarly for our threshold. If you'd like to see the formal semantics, is here. And we also have a local semantics of percentage quantifiers that count only count over successors. So for example, I have a quantifier, there exists k% of R X's phi, which means that whenever I have an X, I count over successors, are successors of X, and there must be exactly k% over them that satisfy phi. And again, the semantics is here, but you can check the details on the YouTube channel. And notice that it doesn't make sense to consider, for example, global percentage quantifiers over infinite structures, because what should it mean that I have, for example, at least 70% of elements satisfying phi? There can be infinite, they can be infinitely many of them. So everything trivializes over infinite structures, but it makes sense to consider local percentage quantifiers over finite branching structures. So when the number of successors is finite. And our results are as follows. So first of all, we will show that the finite satisfiability problem for the two variable logic with percentage counting is undecidable over any of the semantics, so either global or local. Then we will show that the same holds for the guarded fragment. So we meet in the middle and we consider the two variable guarded fragment, which is defined as the intersection of FO2 and the guarded fragment. And this logic is still expressive enough to capture, for example, ALCI and standard model logics. And in this case, we will show that the finite satisfiability of the guarded fragment with global percentage counting is undecidable. But on the other hand, when we focus on local percentage counting, the logic retains decidability. So for finite branching structures, but structures that can be possibly infinite, we managed to show exponential time completeness of the problem. And this is done by some kind of Tableau algorithm. And we also focus on the problem of conjunctive query entailment, which is popular in description logic segment. And over infinite structures, everything is quite easy, but we cannot really use infinite tree-like structures to reason about finite structures, which is crucial in our decidability proof. So for finite structures, we managed to show decidability of the finite satisfiability problem for GF2 plus local percentage counting in triply non-deterministic exponential time and querying in fourfold non-deterministic exponential time. And the proof is quite complicated, and it goes via reduction to integer programming. And all our positive results holds also if we have more expressive constraints and successors, for example, if we have the whole Pressburger arithmetic. So we can also use modular constraints, we can compare sizes of sets and so on. So, okay, so that's all from my side. Thanks for attention, and I'm happy to answer questions.
Yeah. Hi. Thanks a lot, Bartosz. Yeah, so are there questions for Bartosz? As always, please raise your hands. We have, thanks to Bartosz finishing perfectly on time, we have time for, I think, 2 questions. So please unmute yourself or lift your hand. Any questions? No? Okay, I have, yeah, Mikhail. Let's let Mikhail go first, and then I'll ask one more follow-up. Yeah. I mean, others can also pitch in. You know, this is a conversation between many people in this room. Yes, go ahead, Mikhail.
There is one other decidable fragment of first-order logic is unary negation. I'm not sure if you know this one.
Yes.
So maybe would you think about using percentages in that spirit? So unary percentages, because that might also work. I don't know. That's just a.
Yeah, I think that if you have unary percentages, because the undecidability is because you can use free variables inside this percentage quantifiers, but it's a nice idea. I haven't tried it, but my intuition is that it should be undecidable. But I'm not sure if it's already covered by a work by Tony and the others in ICAP 2020. Maybe it is.
Okay. Any other questions? So when I teach in this online mode, I find that it is easy for me to, instead of asking a question which requires a positive answer, I ask the negative question. If you have no questions, then lift your hands. And that usually makes everybody, wake up, because then I can ask anybody and say, oh, you have a question because you have not raised your hand. But I think we shall not torture people with such queries at this point. If there are no other questions, maybe let's thank Bartosz again. Bartosz has middle of his class. He's dedicated time to come and give us this talk. Thanks, Bartosz. Yeah, so we are now running ahead of time, but let's maybe take a minute for the slide change and move on to the last talk by Yoni. Maybe Yoni, you could share your screen, but we will start in a minute, I guess. Just let's give another minute, Yoni, and then start if that's fine with you. Yeah. Again, given it's online, I think people do join pretty much whenever they want to. All right. Yeah. Okay. So the final talk of this session will be given by Yoni with Tema. And this will be work on continuing on temporal logic, on linear time temporal logic, but with team semantics. And Johnny, the floor is yours.
Thanks. So please let me know if there's some problem with the connection, and I'll turn off the camera, and it should be better then. Okay, so this is joint work with a group of people. You can see them and their affiliations below. And I just wanted to give a short like description of the basic setting, what we are doing, and what we are doing in the paper. And if you are interested in the details, you can always check the paper or send us an email or whatever. So in principle, like the idea in this setting of logics for verification of systems is that, okay, so you have your system that you want to verify, so a piece of software or hardware, and you can then abstract that to a creeper structure, and then each walk or trace or path in the creeper structure will then mean essentially a run of your system. And then you are interested in some properties of the system that you have, or you might be interested in whether your specification is even satisfiable. So I guess in many cases, it might be that people are demanding that you should do something. And if you formally prove that what you are asked is not possible, that might be also a good way forward. Or maybe not, because in practice, people might not be interested in complete solutions, but anyhow. So this is a problem that you probably faced when you have returned from your home office to work. So you turn on your computer and then you want to do something. So the point is that there are two kinds of properties essentially of systems. So trace properties, which are essentially properties of single runs of your system. So for example, every request is granted at some point in the future, for example, or in this example, the computer will eventually be ready. It's a property that a system has is if every run of the system or every trace in the creeper structure has this property. But then you have another class of systems, which another collection of properties which are named hyperproperties, which are properties of sets of traces. So like the computer will be ready in a bounded time, or your system will terminate in bounded time, or any kind of this kind of systems have like properties that cannot be really traced back to single properties of traces, but you really need to consider different traces in collection. Good. So there is a basic system of how to create this kind of logics for hyperproperties, and that is essentially just you take your logic for trace properties like LTL, mu calculus, CTL, whatever, and then you add trace quantifiers. So then you can say that there exists a trace such that for all traces, something happens. And that will allow you to talk about properties of sets of traces here. And since then you have essentially this kind of first order kind of access to the traces. Okay. Another approach to this kind of properties of hyperproperties is Esteem Semantics, which is essentially been studied the past, let's say, a decade, where the idea essentially is to lift your semantics to this kind of properties of sets of things. So like in first order Esteem Semantics, you lift from first order assignments as your satisfying element of your formulae to sets of first order assignments, or you can think from the direction of database theory that you are not talking about properties of records, but properties of database tables. And when we go to these kind of trace properties or hyperproperties, we realize that essentially these hyperproperties are the same thing as theme properties. So if you start with an LTL setting and you start considering logics that you evaluate on sets of these objects or sets of traces, you end up with the same setting of hyperproperties, essentially. And here you can see the difference. So in these hyperlogics, you start with taking these trace quantifiers and then you work with that. But in this Esteem Semantics setting, what you do is that you take the same syntax of your logic, but you lift your semantics to talk about sets of traces. So T is now here a set of traces, and you define the semantics of your connectives with respect to these sets of things. And once our formulae really talk about sets of things, we can add this kind of additional statements, that essentially atomic statements that talk about these kind of sets of things. So for example, dependency or independence or things like that. And then this, in a sense, you can see this as a bottom-up approach to construct a logic. So you start with those atomic statements that you want to be expressible, and then you build a logic up from those basic things. And like here you can see the basic difference of the setting. So hyper LTL is this kind of first order kind of approach to hyperproperties. So you quantify traces, and then you say some property here. And essentially the point is that this formula here really talks about only these traces that you quantified here. So some bounded number. And in Esteem Semantics, so here you can see the two different like the main things here. So we start by evaluating on the whole set of traces, and then the evaluation is this kind of a synchronous. So for example, this future A means that in this part of the team that you satisfy that we are considered here, A holds in some common step in the future. So you are evaluating on the set of things, and a disjunction is then this kind of decomposition. And it gives you a different kind of expressivity, essentially. So what do we do in the paper? Essentially, we argue that this kind of Esteem Semantics approach will give a pure modal logic for hyperproperties, so no first order quantifiers that might have similar benefits than LTL and so on have in the classical setting, if you compare to like first order logics on traces. And then we essentially compare the expressivity and complexity of our setting. And like here, you can see some of the complexity results, mainly what we have, essentially that we get some decidability results when we restrict our logics enough, but quite early on, we get undecidability, or even high undecidability. And so I think this is the most interesting desirable fragment. So essentially the point is that we restrict the untils and weak untils to such way that the thing that happens unboundedly many times is a trace property, essentially. So if we consider this kind of formula blah until blah, in a set of traces, it says that some trace property holds until we get this kind of hyperproperty. That's essentially the thing that makes things a lot simpler. But it still is a quite expressive logic. So you get, for example, the full future operator for any formula, for example, but globally is restricted to these kind of trace properties, for example. Good. I think we are now in time for Nikolai's question, and then we can wrap up. Thanks a lot for the listening, and I have here some connections to logic and the semantics if you are interested in those.
Okay. Yeah, Nikolai, the floor is yours. Okay, so just one second. So what is this V inverted V? What is the symbol referred to?
Sorry.
So could you just explain what is K coherence as well? So this slide, it's not clear what your restrictions are, right? I mean, clearly because you didn't have time.
Yeah.
But maybe a little bit more insight into that since we have a couple of minutes. Could you explain what is K coherence as well?
Yeah, so this K coherence is a really like it's a big restriction. So like a collection of things satisfies a K coherent property if and only if every sub collection of it of size at most K satisfies it. So it's a quite big restriction. So essentially how I interpret the result that we have essentially here, that if we take the K-coherent formulae of this very powerful logic, which essentially can define everything in this team setting, then we get only this hyper LTL universal fragment. So essentially what it means for me is that that the interesting things that you can express in this logic are not K-coherent, essentially.
I see. Okay. Are there other questions? Please lift your hand. We have maybe a couple of minutes. All right. If not, okay, I'll just ask one more question since I'm curious. So is there other examples? So could you maybe motivate a little bit on, so an example of a property in team LTL which would not be easily expressible in, let's say, some more standard. So what is the, motivation of this team semantics in terms of expressivity?
Yeah, so one classical example is that something like if you have an infinite collection of traces or unbounded size collection of traces, then you can say that that something happens in bounded time, for example. So there's a uniform bound for all the traces such that something happens, or something happens in all the traces at the same time at somewhere in the future. So in this kind of unbounded number of, so you can like we are proven here is that if we allow this kind of unbounded MSO quantifiers essentially. So if we allow to quantify arbitrary subsets of the infinite trace sets, like if you take the traces and take them as a first order structure with like uncountably many copies of like traces and you wind them up all in the first order structure. Then if we use an MSO quantifier there, then we can do everything that we can do in our logics here. But that's essentially a big stretch. And some things, if we go to properties which are essentially downward closed, so if a collection satisfies it, any sub-collection satisfies it, then we can get a bit simple fragments of these hyper logics, but we still need this some kind of MSO quantifier here, or if we have this left flatness, then this kind of quantification of phrase proportion symbols. So this would be a uniform MSO quantifier that gives the same truth value for each fixed time step. So we have this so it lives somewhere below this kind of MSO scope of things.
Okay, thanks. All right, thank you. Okay, so I guess we are at the end of the session. Thanks, Yoni, and thanks to all the speakers for a very nice, even a short session, and hope to see you in the rest of FSTTCS. Over to you, I guess, Nikolai or Prince, who is the local, yeah, thanks.
So just we reconvene in 15 minutes at 1:15. So thanks a lot for the speakers of this session, and see you in a moment. But feel free to stay here if you want to recreate a virtual coffee break or something.
Yeah.
Thanks, Akshay. Thanks, Nikolai.
Hey, thanks, Deepak.
Thank you, Akshay, for sharing.
My pleasure. Yeah.
So I think I have 8 minutes, right, for the talk, and then 3 or 4 minutes for questions.
Yes. These are the rules. Yes. Yes. 8 plus 4. Yeah, so let's just wait a few seconds so that we can begin on time.
So do you see it, for instance, the change of the slides, right?
Yes,
now
everything seems to be working fine.
Thank you.
Yes, we are good to go, and actually it's time to begin. So welcome to session B2 at FSTTCS. My name is Andrzej Murawski, and I'm the chair of this session. We're going to have 4 talks. The time limit is 8 minutes for the talk, and then 4 minutes for questions. The first talk is related to a paper by Raúl Gutiérrez, Salvador Lucas, and Miguel Vitores, and the title is Confluence of Conditional Rewriting in Logic Form. And Salvador Lucas is delivering the talk.
Okay, thank you very much, Andrei, for your presentation. Yes, this is a joint work with Raúl Gutiérrez and Miguel Vitores. And this is a work on proving confluence of conditional term rewriting systems. If you are familiarized with term rewriting systems, then conditional rewriting systems are just the extension of rewriting systems where you allow for conditions in the rules, and then these conditions are used to decide whether the rules should be applied or not. And then what we want is to investigate confluence of these systems, and confluence, as you can see in the slide, is a property that essentially guarantees that if you start from a term S and you may go from S to 2 different terms T and T prime, for instance, by using many rewriting steps, then you can join together these 2 terms T and T prime into a single one U. So if this holds, then we say that the system is confluent. There is a weaker property, which is local confluence, where you only allow for one step in the beginning, and they are both related, actually. But in principle, the most important one is confluence, because it guarantees that, for instance, you can define a semantic description for the conditional term rewriting system, where, for instance, all terms have a single normal form, if any. So this is a main reason for which this property is important. So we are investigating this property in the paper. If we take a look, a more closer look to the conditions of the conditional rules, we can see that they have this shape that you can see in the slide. They are pairs of terms which are related with some equality-like symbol. And actually, this equality-like symbol hides different ways to evaluate these conditions that you can use. For instance, you can use this. You can evaluate the conditions using reachability tests, or using joinability tests, or combining them by using conversion relation. And you can also associate a first-order theory to these conditional term rewriting systems, and this first-order theory will, of course, depend on the kind of evaluation of the conditions you may want to use for defining the one-step and many-step reduction relations. In any case, whether the first-order theory could be based on reachability or joinability or conversion, you have a single way to define one-step and many-step rewriting by using provability, as you can see in the slide. And this is an example of how to obtain this first-order theory from a given conditional term rewriting system. You can see that we have essentially four groups of rules. The first one defines that many-step reduction is reflexive. The second one, compatibility between one-step and many-step reduction. The third block of rules or sentences says that you can propagate reductions below symbol F in both arguments. And then we finally have the representation of the three rewrite rules as first-order sentences. So now one of the contributions of the paper is the fact that we want to have a characterization, a logic-based characterization of confluence of rewriting, and we can do that by using a canonical model. We cannot do that by using provability, as we show in the paper, but we can do that by using a canonical model, which is obtained from the one-step and many-step reduction relations by just combining the terms that can be rewritten and grounding the variables in the terms by using new constant symbols, as it is explained in the slide and in the paper. And then, provided that we use this model, this interpretation of the systems, we can formally define confluence and local confluence as satisfiability of these formulas, these first-order sentences on this model. Okay. And then now we move to the analysis of confluence of these systems. And for the analysis of confluence of conditional systems, we use conditional critical pairs, which are obtained from the rules. And another important result of this paper is that we can characterize joinability of these conditional critical pairs by using this model that we have introduced in the previous slide, as satisfiability of a first-order formula in this model. And then now what we do is to use these facts to obtain a method to prove and disprove confluence of conditional systems. So there are a number of confluence criteria in the literature. For instance, if you have a non-joinable conditional critical pairs in a system, then we know that this is non-confluent. If you have a joinable critical pairs in the system, then you can prove confluence, but you often need to add some other conditions. So the point of this paper is that we center the attention, we focus on the on the problem of proving joinability and non-joinability of conditional critical pairs. And for that purpose, we use other logic devices, like, for instance, proofs of feasibility that we have investigated in other papers this last year. So we have a number of results showing that you can translate joinability of conditional critical pairs into feasibility problems or provability problems using the first order theory that we discussed before, and the sentence that characterizes joinability of conditional critical pairs. And you may also disprove and prove joinability of conditional critical pairs using feasibility tests, as shown in the slide. So we have used all these things to implement a new tool for proving confluence of conditional term rewriting systems that we have tested in the international competition on Confluence this year. So we get good results in this competition, as you can see in the slide. And then these are essentially the contributions of our paper. So we are able to deal with different kinds of conditional term rewriting systems using different first order theories, but we can define confluence and joinability of conditional critical pairs using the model that we have introduced, which is obtained from this theory. We have implemented everything into a new tool that it works quite okay. It has been successful in the last Confluence competition, and as future work, we plan to extend this work to Mod language, which is a rewriting-based programming language. So that's all for the presentation that I wanted to make. And now, if you have any question, I will be pleased to answer.
Okay, thank you very much. Also for finishing on time. Thanks a lot. So I think there is a way to applaud on Zoom, but yeah, so feel free to use this option. Yeah, thanks, Mikoy. And right, are there any questions? Let me check. I cannot see any. So let me ask one. So you had a slide about these competitions for detecting confluence, and I think from the slides one can tell that the tool is doing very well when it comes to certifying confluence. Can you say a few words about the complexity? Is the tool more or less efficient than the other ones?
Well, actually, one of the main points of this tool is that we use a number of other related tools to obtain our proofs. Okay, so in particular, we use InfChecker, which is a tool for proving feasibility properties. We also use Muterm, which is a tool for proving and disproving operational termination of conditional systems. So this makes that our proofs may involve to do a number of calls to these other tools, and this makes it maybe a bit slower. Okay, so we have to work on that point in the future.
I see. And just roughly, what kinds of run times are we talking about? I mean, how long does it take to verify the most complicated case?
Well, actually, there is a timeout in the competition, which is 1 minute. So everything must be done in 1 minute at the most, you know. So we are fast enough as to get these good results. But still, there are proofs where we take much more time than other tools, and this could be improved in the future. Maybe we took 30 seconds, and other tools maybe took 5 seconds. So we can try to improve this point. Yeah.
Okay. Thank you very much. Are there any other questions? I think that don't seem to be any. Thank you very much for giving the talk. And my understanding is that there is a fuller version of the talk available online, and everybody can learn more about this topic. Thank you very much, and we move on to the second talk of the session. Thank you. So the second talk is related to a paper by Kentaro Kikuchi and Takahito Aoto, and the title is Simple Derivation Systems for Proving Sufficient Completeness of Non-Terminating Term Rewriting Systems, and Kentaro is giving the talk.
Thanks for the introduction. This is a joint work with Takahito Aoto. In this presentation, we will talk about sufficient completeness of term rewriting systems. It means that every computation by the TRS produces a value that is a term consisting of constructors. For example, let's consider a TRS RR for addition of natural numbers. By this TRS, every ground term that is a term without variables can be written to a value S of blah 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 S of 0, where S and 0 are constructors. Sufficient completeness has various applications. In particular, it is useful for proving inductive theorems of TRS. In this work, we present a simple derivation system for proving sufficient completeness of possibly non-terminating TRS. We also present variations of the derivation system for proving two kinds of local sufficient completeness of TRS. Now I'll introduce a derivation system for proving sufficient completeness. First, I'll explain some terminologies. We assume function symbols are divided into constructors and defined symbols. Ground terms are terms including no variables. Ground constructor terms are ground terms with only constructors as function symbols. A ground substitution is a mapping from variables to ground terms. Then a TRSR is globally sufficiently complete if for ground term T, there is a ground constructor term V such that T arrow star V, where arrow star means the reflexive transitive closure of arrow R. That is, T rewrites to V by 0 or more rewrite steps. In the example of the TRS RR, we can say RR is sufficiently complete since that condition is satisfied. For example, the ground term expressing 1 plus 2 plus 1 rewrites to the ground constructor term expressing 4. Our derivation system consists of rules to manipulate a set of guarded terms. Each guarded term, T vertical bar H, is a pair of a term T and a set H of terms. The derivation rules are 4 kinds. Each rule derives a set of guarded terms from a set of guarded terms if the side condition is satisfied. The decompose rule decomposes a term with a constructor as its root symbol. The expand rule substitutes a variable x in T by each pattern with a constructor as its root symbol and produces the same number of guarded terms as the constructors. The simplify rule applies the rewrite rule of R to the term T. The delete rule removes the guarded term T vertical bar H if T is less than some U in H with respect to a suitable well-founded order. We write gamma leads to gamma prime when gamma prime is derived from gamma by one of the derivation rules. Here is an example of a derivation. Let R be a TRS for computing a double of a natural number. We show that d of x vertical bar, the singleton set of d of x, leads to the empty set by some derivation steps. In the first derivation step by the expand rule, the variable x is substituted by each pattern with a constructor as its root symbol, where 0 and s are constructors. In the next steps by the simplify rule, Rewrite rules of R are applied to the terms on the left of the vertical bars of the guarded terms. In the next steps by the decompose rule, constructors at the root are removed. Then after some steps by the simplify rule, the delete rule is applied, where we use a lexicographic path order as a well-founded order. Now our theorem for proving sufficient completeness is as follows. A TRSR is sufficiently complete provided h of x vertical bar the singleton set of h of x leads to the empty set for every function symbol h. And the order is a lexicographic path order induced by some precedence on function symbols such that every defined symbol is greater than every constructor. An example of applying the theorem is that the TRSR for computing the double of natural number is sufficiently complete. Next, I'll introduce derivation systems for local sufficient completeness. In this work, we discuss two kinds of local sufficient completeness. Here, we consider one of them, called local sufficient completeness with sort partition. We assume some conditions on the signature of a TRSR. The first condition is that the sorts are partitioned into S0 and S1. The sets of function symbols and ground terms are also partitioned into according to their sorts. The fourth condition says that for every constructor G in F0, all the arguments have to be of sort S0. Then R is locally sufficiently complete on T0 if for all ground terms, term T in T0, there is a ground constructor term V such that T arrow star V. As an example, let's consider a signature with sorts N of natural numbers and L of lists of natural numbers. Function symbols include some plus from as defined symbols and 0 is nil cons as constructors. Let R be the TRS with rewrite rules for the functions sum, plus, and from. The intention of this TRS is that sum of NTS computes the summation of the first n element of a possibly infinite list TS. This TRSR is not sufficiently complete, since the term from of 0 induces infinite computation and cannot rewrite to any ground constructor term. However, we can show that R is locally sufficiently complete on the ground terms of sort NAT. The derivation system for local sufficient completeness with sort partition has the expand rule modified from the previous one. The variable x is substituted by each pattern with a constructor or function symbol in F1 as its root symbol. Our theorem for proving local sufficient completeness with sort partition is as follows. In conclusion, we presented a simple derivation system for proving sufficient completeness of possibly non-terminating TRS, and the variation of it for proving two kinds of local sufficient completeness. This will conclude my presentation. Thank you very much for your attention.
Okay, thank you very much also for sticking to our time constraints. Are there any questions? I cannot see any hands in the air. So I was wondering if was wondering about the applications of this notion that you were studying. So sufficient completeness. Could you comment on this? When would one be interested in checking this property?
Yes, this is useful for proving inductive theorems of TRS. It's an equation on the initial algebra.
Mm-hmm. Oh, so
Actually,
does this mean
is combining with Confluence in the previous talk. Right.
Oh, I see. So these systems could be used in algebraic specifications.
Yes.
I mean, tools that can reason about such specifications. And right. So would the tool mod be relevant again?
Yeah, yes. But our results are not a conditional system.
I see. So are there any specific examples of tools, I know proof assistance, in which you would like to implement these systems you introduced?
We have not yet implemented the techniques as a tool. So,
but would you? I mean, is this something you would be interested in, or do you view your work as pure theory?
I'm thinking of applying this technique for proving equation on, for example, lazy evaluation language. Because in that case, so infinite lists can be written as a non-terminating expression. So we are thinking of functions of this kind, including non-terminating expression.
Okay, I see. So there are links to both algebraic specification and lazy evaluation.
Yeah.
Okay, thanks. Are there any other questions? I cannot see any, but our time is also up. Yeah, thank you very much for this talk again, and for respecting our time limits. Let us now move on to the third talk in this session. So this is a paper by Donggo Li, Valentin Perel, and Benoit Valéran, and the title is A Concrete Categorical Model of a Quantum Circuit Description Language with Measurement. And I assume that the first named author is giving the talk. Please feel free to start. Okay, we cannot hear you. You may be muted. So Donggo Li is, I think Donggo, you're still muted. Oh no, you're alive. Okay.
Hello. Sorry
Hi.
for that. Hi. Thank you for the introduction. And I will start the presentation. This is a collaboration with Valentin Perel and Benoit Valéran, who are my supervisors, and Xiaowei Xu, who was a postdoc at LMF. So to begin with, I'd like to give you some context. Our work is based on Theorem model, which is a model of quantum computation, consists of two parts. first classical computer does a classical computation and produce a quantum process which is transferred to quantum coprocessor. And then there is a quantum coprocessor who receives the process and simulates it and return the classical data to the host by observing the quantum state. And one implication of this model is quantum computation can be statistical set of quantum computation. And this property is related to dynamic lifting. In specific, it means that information can be transferred from the quantum coprocessor to classical host and then can be used in a circuit construction. So as an example, you can have a term X, which measures a qubit VC and stores the outcome in the pair of a Boolean B and qubit called VC, and it can create different circuits depending on the value B. In this, so now quantum circuit construction can be dependent on the result of measurement. And this is a feature of several quantum circuit description languages which is already there. However, its formal semantics is not well studied. So in our work, we asked two questions: how to formalize dynamic lifting in operational semantics, and what is a categorical representation of dynamic lifting for a circuit description language. And we use the fact that dynamic lifting creates multiple control flow in classical computation. So to begin, we want, in order to formalize dynamic lifting, we need to have a formal language. To do that, we start with defining an algebraic structure of quantum channel called QC-arg. The definition you can find, we have measurement constructor, which is followed by quantum channel object Q1 and Qc. And then we define a formal language for dynamic lifting. Because of the non-deterministic effect brought by dynamic lifting, the language has a two-part, non-branching and branching term. The term is not different from other quantum circuit language, except that we replace the quantum circuit constant with quantum channel constant, which can be found in the middle of the first row. And you can also see the quantum circuit operator box and non-box. And then the branching term is defined as either a term M or a pair of branching terms. And we also have a linear, non-linear type system, which ensures that quantum data is used exactly once in a term. And also the type system ensures that all terms of a branching term share the same type. So to give you some example, there are two typing derivation rules for quantum circuit operators box and non-box. And you can see that we have a type for the quantum channel objects called Qchen, depending on the input type P and output type A. So to formalize the dynamic lifting, we define operational semantics, which is a circuit buffering, we call circuit buffering abstract machine, which buffers quantum channel while reducing the term. In this abstract machine consists of a configuration and a set of reduction rule or transition functions over configuration. And configuration is represented by a pair of a quantum channel object Q and a branching term M. And we represent the configuration graphically using the green box, which represents a quantum channel whose leaves are linked to the square box terms, which represent the branching term. In the figure 2, you can see the configuration representing graphically, where it shows a measurement applied to a qubit W, and you can see that it creates a measurement constructor in the quantum channel object in branching term with two leaves. And the reduction takes place in each branch of branching term. and it proves the type safety property of the language. In order to do that, we extend the typing judgment to the configuration. And type safety property consists of two lemmas, subject reduction and progress. Subject reduction lemma states that the type of a configuration is preserved over the reduction. And the progress lemma states that for all well-typed configuration, the configuration has a reduction or it is a value. And now we move on to the categorical semantics of dynamic listing. I will give you a brief overview of the model. And our model is based on two other works. One from Product Keeper M by Francisco Rios and Peter Selinger, where they create a model for parameterized circuits. And they begin with the symmetric monoidal category, which is a model of graphical languages consisting of boxes and strings. And they make a symmetric monoidal clause category by a compilation, which models a higher order quantum circuit, which means that there is an object for a quantum circuit in higher order objects. And they create a co-product compilation to give a model of parameterized circuit. And their model is also based on Benton's linear and nonlinear category, where they can separate quantum data and classical data, and also which allows us to model, interpret quantum circuit operators. And secondly, our model is also based on Moji's categorical interpretation of side effects. In particular, we define a branching monad to interpret the non-deterministic computation by dynamic listing. And the program is then interpreted as a morphism in the Clay-3 category. And furthermore, our categorical model is based on diagram. The diagram is directed graph composed of multiple types of nodes and marked edges. And marks for the edges defined as follows. We have a unit, a cubic cube, a tensor product, and box composition, and a dual. And then the nodes are defined either as elementary node or box node, where the box node composed of a family of diagrams. And the diagram comes with equivalence relation on which we prove the soundness property of categorical semantics. And now the soundness of categorical semantics states that the categorical interpretation of typing derivation is preserved over the reduction. However, since there can be several typing derivation for one typing judgment because of the promotion and dereliction rules, we had to weaken the soundness theorem, and we show the theorem which is shown in the slide. And however, one can note that for the basic type whose values have unique type derivation, the denotation of the terms, closed terms, is independent from the choice of typing derivation. And then we can prove the following corollary, which says that all the typing derivation of a closed term of basic type share the same interpretation. And this is it, and thank you for your attention.
Okay, thank you very much. Do we have any questions?
Oh.
Yeah, so I wanted to ask you about the relationship between this work and possibly the semantics of programming languages that use dynamically allocated resources, like maybe references. So in your work, can you use any insights from this field from analyzing, for instance, high order references in order to well, advance your goals?
Oh, so you're asking the relationship with other.
Yeah, so I was just wondering if, because I mean, you work on quantum circuits, so that's a slightly different area, but there are some similarities to situations where you generate, when a program generates something that can be used later, and there may be cycles as well.
Yeah. Well, I didn't think about this before, so I'm not sure if I have an answer.
Okay, so judging by your reaction, that there doesn't seem to be much overlap at the moment, and these methods that you developed are quite different.
Yeah, perhaps there is a relationship, but I haven't looked into the semantics of the dynamic reference yet, so perhaps I don't know. I don't have no answer. Sorry.
Okay. Thanks. Are there any questions? Any other questions? Okay, there don't seem to be any. So let's thank the speaker again and move on to the last talk in this session. So the paper is by Filippo Bonchi, Alessandro Di Giorgio, and Paweł Sobociński, and the title is Diagrammatic Polyhedral Algebra. And I understand that Alessandro will be giving the talk.
Yes, yes.
Okay, so you're online live. So yes, over to you.
Okay, thank you for the introduction. And as you say, this is a work in collaboration with Filippo Bonchi and Paweł Sobociński. So, given the time constraint, I will not go too much into the mathematical details, but I will focus on the key points of this work. And I will show you what I think is a meaningful example of application of diagrammatic polyhedral algebra at the end of the talk. So in this work, we are interested in a particular class of mathematical objects, which is indeed polyhedra. A polyhedron, I recall you that in its most famous form is described as the set of solutions of systems of inequalities. And in particular, in our work, we look at them in a relational way, meaning that instead of considering vectors, for example, in R to the n plus m, we look at them as the pairs of a relation. So in R to the n times R to the n, for example. So beside this, we focus on, our approach is diagrammatic, meaning that we have a language of string diagrams in which we can faithfully represent any polyhedron. As you can see, the relational structure is somehow reflected by the diagrammatic one, meaning that we have some wires here on the left and some wires here on the right, exactly corresponding to what here I called X and Y. And moreover, the diagrammatic language is compositional. So diagrams are made of little parts composed together sequentially or in parallel. And all these parts are somehow describing the polyhedron itself. For example, here we have the matrices, the vectors, the constraints, and so on. Unfortunately, I don't have the time to explain all of the language and its semantics and so on. Well, finally, the main point of this work is its axiomatization, which is basically a set of rules, a set of equalities between diagrams, which is complete, meaning that whenever two polyhedra are equal, then also their diagrammatic representation is equal by means of the axioms, and vice versa. So one possible application of the theory is to take all the theorems which are usually found in convex analysis of convex geometries that involve polyhedra and prove them by means of the axiomatization, and so in, let's say, in a more algebraic way. Moreover, all these, let's say, four features are not standalone but play well together. For example, I could take a diagrammatic representation of a polyhedron, and since it is compositional, I can focus on little parts of it, for example, the matrix A, and simplify it by means of the axiomatization without looking at the whole, let's say, system. This will be even more clear in the example. So besides the application of looking at polyhedra in this diagrammatic way, we can represent in this language diagrammatically. We can represent systems where there is some notion of capacity or bounded resources. And one example is indeed flow networks, which I recall you are basically graphs where each edge has a capacity. And on these type of graphs, we usually ask for the maximum flow, which in this case is 5, and it corresponds to the minimum cut of the graph. And it is, well, the amount of flow that can go from S to T, respecting all the capacity. So, for example, here we cannot have a flow that exceeds 6, here 1, and so on. So we encode flow networks in our diagrammatic language by translating simply the nodes and the edges. So in the next few slides, I will try a little bit the diagrammatic notation. So given that, we can, for example, state some let's say, properties of flow networks, some transformation we can do. One, for example, is edge contraction. So whenever we have a network or a piece of a network like this, we can contract the two edges with K and Q, or labeled with K and Q, and look at it as a single edge with a K plus Q capacity. And this is easily rephrased in our diagrammatic language as a derived law like this one, which is provable in the axiomatization, of course. We can do something more. So, for example, what I call redundant constraint elimination, which basically when we have two edges labeled with K and Q and an outcoming edges labeled with L, such that K plus Q is less or equal than L, then we can just drop the L. And this is because K plus Q, so the flow will never exceed L, since K plus Q is less or equal than L. Again, this is easily representable in our diagrammatic language by this law that basically removes L from this wire. As you can see here, we have the identity. So given this, we can take the example I showed you before and translate it in the diagrammatic language, and then we can start applying the laws and the axioms of the axiomatization. So, for example, here I can do redundant constraint elimination, since 1 plus 2 is less or equal than 6, and so I can rewrite the diagram where the 6 has been dropped. Again, since the language is composition, I can focus on other little parts of the network and then use again the law and drop the 5 here. Here I can reorder this wire using the fact that these, let's say, white spider is associative, and this is a law of the axiomatization. And then I write it like this. Then I can contract these two edges. I can contract them again and get a single, get a network where we have a single edge labeled with 5, which is equal by means of the axiomatization to the original network. Now, if you recall, the maximum flow of this network was exactly 5, And so what I did is to compute axiomatically and diagrammatically, exploiting the compositional structure, the maximum flow of this network. So to conclude, what we gave was a complete axiomatization for Polyhedra, which, to our opinion, is suitable for automating proofs involving Polyhedra. There are many of them in the literature. For example, you can think of Farkas lemma or linear programming duality, where the constraints are usually easily represented by Polyhedra. And also this, the fact that we can automate proof is that the approach is algebraic, and so let's say amenable to theorem provers. But also, as I showed you with the last example, we can model systems where we have bounded resources or a notion of capacity as flow networks and reason on them axiomatically and diagrammatically. So again, sorry for being very fast, and I didn't introduce all the details that you might want to know, but this is pretty much it, and thank you for the attention. Of course, if you have questions, I'll be pleased to answer.
Okay, great. Thank you very much. And yeah, so these are only very short talks by design, but yeah. The full versions can be watched on YouTube. Right. So, are there any questions? Okay, Mikołaj seems to have a question. Yeah, Mikołaj.
Open-ended question. So, if I understand your diagrams, they represent Polyhedra, and is there like is that correct?
Yes. Exactly.
Is there a diagrammatic language to represent things which can be defined, say, in Tarski arithmetic, in the sense that you have not only linear conditions, but you have like addition and multiplication, polynomial properties? Does that make sense?
Well, not that I know in the literature, but in our framework, not for sure. So the representation is all linear. The inequations are all linear inequations. So unfortunately not.
No, it's just, I mean, thanks. Thank you.
Thank you.
So I was wondering if you tried to use your diagrams to prove some theorems about Polyhedra and whether they would lead to I know maybe particularly elegant arguments. I know, do you have examples of such things?
Yes, actually I have a very particular example that we published in another article where we use this language to prove the Farkas lemma, indeed. And the proof is really beautiful because we exploit the fact that the duality that play a key role in the Farkas lemma is easily explained by color switching of all the generators that compose the diagrams. So basically, you look at a polyhedron as a diagram and switch all the colors in the diagram, you get the notion of a dual polyhedron or a dual cone, actually. So yeah, there is this example, and we also use it for linear programming dualities and so on. So you can write me. I will link you to the references if you're interested.
Okay, great. Thank you. Are there any other questions? Okay, there don't seem to be any, and our time limit is up as well. So many thanks for the talk, and also a big thank you to all the other speakers. So this session B3 is now over. I know if you're interested in a talk in track A, I think there's just one left in their sessions, but in track B we're done. So thanks for your attention and see you in the next session. Okay, thank you.
Have one more invited talk today.
Right, indeed, yes. So don't forget about it, and be careful about